In this short tutorial, I'm going to demonstrate how to use the anisotropic energy degradation element. We will create two separate finite elements, one with an isotropic and one with an anisotropic energy degradation or asymmetric tensile or compression energy release properties. We will have a load which looks like this. First, we will extend our elements until 1% strain, then we will compress it to minus 2% strain, then extend it further on, and we will see how the two elements will respond and what is going to be the difference. In this tutorial, we will see the effect of the asymmetric energy degradation. Additionally, we will see how to define several materials in one model and convert the script using a MATLAB file. Let's get started. After opening the MATLAB graphical user interface, simply click on the standard explicit model. Make sure that your work directory is set correctly, then click OK and save the model. Let's name it ANISO. Press enter or OK to confirm your name. Then in the part module, we will create a part. Let's name it as usual sample, set it to 2D planner, leave it undeformable, it's a shell, and let be the size 10. Click continue. Now we are at the sketch module. Let's create two elements. The first one will be 0.20 until 1.2 and 1. The other starts at minus 0.20 and extends until minus 1.2, 1. When this is ready, click on the red X and click done. We can see that in one part we have two elements. These are going to be then processed further on. Let's click to the property module. Let's create our UMAT element where we have a user's material with a very small stiffness and an arbitrary Poisson's ratio. We will add user dependent variables as usual. This is going to be 16 as well. Let's click OK. Let's create our section. This can be left as it is. Click continue. Make sure that the material is the UMAT element which we created earlier. Click OK and then create and assign the created sections to the part, or actually to the sets. Here we will create two sets. First one is going to be the isotropic set. Let's select the left element, click done. Make sure that the section which we have selected is section 1. The second one is going to be the anisotropic set. Select the right part, the right element, and click done. And click OK. We do not have any other sets to select, so terminate the command. If we go to the assembly module, we add the assembly by creating an instance. We shall accept everything. Let's click OK. When we are at the set, we will see that we made two different sets. These sets are going to be then assigned with the material properties in the MATLAB file later on. Let's create additional sets where we will have the boundary conditions. The first one will be the bottom. Here we can select both bottoms because we will have the same kind of constraint. By double clicking on the set menu here, we have sides, click continue, select all 4 slides by holding the shift key. Yes, they are highlighted. Let's click done, and the top finally. Similarly, click continue, select the first, hold the shift, and select the second one, click done. So we can see we have a bottom set, a side set, and the top set. In the next module, we will create the simulation step, the analysis. This will be a static general analysis. By clicking continue, we can set the incrementation, which will be, as usual, fixed. Let's have 1000 increments with 001 step size. Click continue. Don't forget to save your model. The output what we request shall be the displacement and the reaction forces. Click continue and dismiss this window. Step now on the load module, where we will create the boundary conditions. Create a boundary condition, name it the bottom boundary condition, which will be a displacement rotation boundary condition. A pre-made set will be used to assign this. This is going to be the bottom. Continue. Here we will constrain the translations, the displacement in the y direction, which is the second direction. This will remain 0. Then we will add the side boundary conditions, which will going to be a displacement rotation boundary condition again on the side set, where we will constrain the x directional displacement, so the first degree of freedom. We will see all 4 sides are now constrained. Now we will add the load on the top. Let's scroll down, select top. This will be elongated or compressed in the second direction with an amplitude of 1. However, we will define a table here. At 0 time, we will have 0 amplitude. At time 0.1, we will have 0.01 amplitude. At 0.4, we will have minus 0.02 amplitude, and finally at 1 we will have 0.04 for the amplitude. Let's click OK. Make sure that you select your actual table and click done. Save your model. Now go to the mesh module, where we will assign the mesh to parts. Here let's add a basic seed where the size is 1. Thus we will have only 2 elements. Mesh the part and click yes. Now we are ready. Go to the job. Let's create your job. Let's name it an ISO. Let's click continue. OK. In the job manager, ask Abaqus to write an input file, and then go to the MATLAB program. Here we can see that the input file has already been created. Make sure that you downloaded the Abaqus script with the new Fortran file with the anisotropic energy degradation. Let's create a new script. This will make our lives easier. Let's type Abaqus to phase field UEL aniso. what do we need in this file? Let's open it. First, we will give the name in a string, the input file, then the material properties. Here we need to give 7 material properties: the Young modulus, the Poisson's ratio, the thickness of the element, the stability parameter, and the additional parameter is a switch variable which decides if the energy is going to be degraded in an isotropic or in an anisotropic way. And then the usual length scale and fracture surface energy release rate. So go back to our file, let's save it, let's name it test. The name of the input file is aniso.inp, where we will have the material parameters, and this is going to be a matrix. Material parameters, which will have 2 lines, as we had 2 materials in the original model. First, we will have Young modulus, Poisson's ratio, the thickness of the element, some kind of stability, then the switch. The first element we defined is the isotropic switch, isotropic element, isotropic energy degradation element, so we will have 0 here. Then let's have 0.1 for the length scale parameter and 2.7 times 10 on the minus 2.7 for the fracture energy release rate. Then click enter, and let's add the second material, which is going to be almost the same. However, we will change the degradation to anisotropic now. Let's close this matrix. Theoretically, we have all the material parameters what we need, and run the script. After running the script, the MATLAB file will create the new input file with the Fortran file, which we can then use in Abaqus. Let's create a new job, use an input file, select the newly created input file, click continue in the general tab, select the Fortran file for the subroutine and click OK. Now submit it, and we will see that it is going to be ready in no time. One additional comment before watching this result file concerning the material definition with the sets. These materials are given in the same order as we defined the original sets. So when we open the original input file, we will see that first we define the left material, which is going to be the isotropic material, and then secondly we defined the anisotropic material. So we have to keep the same order here as well as we did the original definition in Abaqus. Now we are ready to view the results. Click on creating an XY data. From the ODB field output, click continue, select the Y directional strain, which is the 4th solution dependent variable, and the 10th, which is going to be the stress in the same direction. Leave it on the integration point. In the element selection, edit the selection and first highlight the isotropic energy degradation, and let's click plot. Dismiss this window. What we can see here, if we combine the two data, so the strain and the stress, let's see, combine, first select the strain, then the stresses, plot it, cancel, we will see that after a certain loading, when the degradation starts to appear, we decrease our stiffness and both our stress to a certain point. Then when we return, we inverse the deformation, so we start to compress our material, it goes back on the same slope, then reaches approximately the same value, same strain value as we had, and stress value as well as we had under extension, and the material starts to degrade further on. And when we inverse the deformation, so we start to extend the material, it will remain elastic until the same strain, however on the negative extended part, and then degrades further on. Let's report this into an XY data, select this temporary data which has been plotted, click on setup, and let's say stress strain isotropic dot txt. Let's not append, and then click OK. This simply created us a txt file where we have the data, the stress data as function of strain. Now let's go back to our element. We do the same for the right element. We leave the 4th and the 10th solution dependent variable. Let's go to element, edit selection, select the right one, and click plot. Dismiss the window. We can immediately see that on the compression side this remained elastic. Let's combine the two data. Click continue, combine first the strains and the stresses, and plot the expression. Exactly after the extension, after degradation, when we start to reverse our deformation, we return to 0, and then we achieve the same kind of elastic stiffness as we had initially. Let's report this data as well. Make sure that the temporary file, the temporary data is selected. Go to setup, and this is going to be an isotropic txt. Click OK. Now we can go to an Explorer window, and we can select these two files. First the isotropic, select all, tap Ctrl C or Ctrl copy, go to an Excel window and paste it. Click on data, text to column, click next, and select space as the delimiter. Click finish. We will do the same for the anisotropic one. Select all, copy it, go to the Excel window, and now by simply pasting it we will have the same delimiters. Now delete the first two lines, shift the cells up. This was isotropic and this was anisotropic. Select first the two columns and insert a diagram. We will do the same with the second one. Select this curve, Control cut, select the first diagram and paste the curve in it. Let's set our limits that we can see the data. Select the anisotropic curve and change it to black, for example, let's say yes, and dashed, that we will able to distinguish between the two curves. What can be seen is on the extension side we have the same kind of behavior for both elements. After reversing the deformation and reaching 0, the anisotropic element will continue with the same stiffness as it had originally. However, the isotropic degradation function will have the slope, the degraded slope. It actually damages further on compression, under compression, and then when we return our load, the anisotropic function will go in the same slope as it returned. However, the isotropic one will have the slope which is further on degraded on the compression side. When we reach 2% extension strain, the two curves will overlap and the results will be the same. Finally, to conclude, in this tutorial we saw how to define different materials and how to convert them using the MATLAB script, and we compared the behavior of an isotropic and an anisotropic energy degradation element, both on the extension part and on the compression part. Thank you for watching.